back. Let's see. Okay. Now, let's see. So I'm totally crazed today, as you can see. Here's the. So these are all these things. We may get to some of this. Well, there's maybe half of you here as last time, but actually you already look better. I guess it's a sign. I was thinking how I had this strong impression. Well, I'm kind of run down from a cold, and I had this strong impression that I was really killing you off last time. I just didn't really, your faces, you can all do this game like if you can watch and see what I do. I'm sure I'll respond. If you want me to be like this, right, the thing you do is whenever I'm over on this side of the room, you look bright and alert and smile at me. And when I'm over here, you look tired and you frown and so forth. And then you watch as the period goes, I never leave this side of the room, right? So you get so little experiments. Actually, John, you should be, are you an expert on this stuff? Yeah. Okay, so sort of a social science psych background, you might be really keyed into this stuff. I had this strange thought. Well, this was about 3 o'clock in the morning when I was a little crazed. So this is let's see, 1, 2, 3, 4, 5 things floating around in these file folders. Now, homework 4 back, so whatever we've gotten is being returned, and some lucky few have earned the right to get us to pay special attention to your homework. Okay? So that actually could be good if you're getting some feedback when you have stuff going in. Whatever. It's okay. Homework 4 is coming back, so you should be circling around. There's the intended problem for today, which we will may get to, may not get to. If we don't, we'll continue. This is Constantine going fishing. It's good that you're here in this thing. Now, actually, okay, we'll come back to that. While we're doing that, I want an input from you. This has to do with Constantine. I want you each on a piece of paper to write down 3 kinds of fish that's familiar to you that you would eat. Sort of routine fish that's routine for you to eat. Not so much right here, but like when you're at home. What would be for you familiar fish to eat? I've been talking about this, and I've been wanting to do this experiment, so I want you each to write down sort of 3 fish that you think of as sort of standard fish. I'm kind of interested in what what people will say. That's background to number 2. Okay, so if you haven't got the exams and solutions, they're here to be picked up afterwards. Okay. Well, these things. So I'm kind of I'm letting people get here, so I'm kind of staggering around until the room sort of fills up, right? I'm stalling. This is all of chapter 5 on one page, sort of view of that. This includes the exponential distribution and the Poisson process. Well, it's not everything, but there's a lot of things that are on one. So there's just one page. Of course, if it's a concise summary, it has to be on one page. But here, this is coming around. So there's a sheet that tells you is a one-page version of chapter 5. I mean, there are a few more things to know than that, but anyway, that's something. Okay, then we have this. This is some, these things are on the web page also, so it's redundant, but I'm just giving it to you. So if you have a harder time resisting, it's given to you in your hands in hard copy, and it's sitting on the web page, so you can't, it's hitting you in every direction. Now, this was this epiphany that I had. This relates to the epiphany that I had at 3 o'clock in the morning of remembering your sad expressions last time and thinking, what would really liven up the class? See, I was thinking of what would liven this up, and I had this version. It occurred to me, and it also relates to what I thought we'd discuss the Poisson process today from this point of view, but I had this version of You Bet Your Life. Now, this is a kind of reference point. So I guess what I'm trying to do here is something like this, and then so what am I doing? What is this? Yeah, bridge. Yeah, and it's a bridge, and this is a CE class, and so I'm trying to build a bridge between the generations. Okay, so that's this, where you probably don't know what this is. See, so this is an opportunity to bridge a connection to. Actually goes back to before television. So when you could listen. It's hard to believe there was a time before television. That's enables some of us not to have, if we are not completely brain dead, that's perhaps the reason that we didn't have television then. But anyway, so this is you and me, the generations. Okay, so we have this bridge. And that has to do with this problem. Okay, so this might be the useful thing. The question is, what is, the class is going to be, okay, so this may actually be the most useful reference. So at this point, so if somebody was really an aficionado, the person I want to refer to is George Fenneman. Who is George Fenneman? Okay, see, this is, if you were a real trivia, you would know who George Fenneman was. And he would say, then you'd also know what he would say at this moment. He'd say, here he is, the one and only who? Now that part's getting easier. No, he is George. That's what George's saying. It's a good try. You're in the spirit. But George says, here he is, the one and only. What? Groucho. Okay, this is this. This is this show, this TV show, 1954. I was alive in 1954. I was actually 12 in 1954. Okay, but this you could see Groucho. Now, he had this quiz show. So it's sort of like the line in the quiz show. And one part of this, and this, there's a reference there, there's online. So you just Google this stuff like everything else, and you'll see all this stuff there. So these links, this page, there's a page that gives a couple of links, which is what you get when you just Google. And there's one of the shows where this woman appears, the two people appear, the woman, and with her is God. And it's sort of a nice, it's a nice sample of this thing, so it's really good. I mean, but then, you may think it's just nuts, so this is where the bridge comes in. But in this show, every time, there was a secret word. And now that's what I was thinking. So the secret word was, like, in this show with the God, which I listened again and was reminded was great, the secret word was clock. And the idea is that if the contestants, during this quiz show when they're being interviewed, the interview's the best part about it, the questions are nothing. One of the questions is who's buried in Grant's tomb. That was, we discussed last time. But if they say the word, so in this case, the secret word was clock. So then you're entertained by, in fact, wondering. So then, in part, some of the questions are trying to get the contestants to say the secret word, which, of course, gets key. You're kind of partly helps your interest along. So then, at some point, they ask. The way they get it is what is time? And the secret word, of course, clock, right? So what is time? And God says that's something that you measure with a clock, right? And then at this point, when you say the secret word, this yellow paper mache duck drops down from the ceiling and awards, and you win a $50 prize, right? This is the secret word. Now, my thought is my variant of this game was, this is totally crazy. God, this is totally nuts. But I'm at 3 o'clock in the morning, I'm thinking, gee, if you each, unknown, see, I don't even know, but you each, you have decided, you got together, and you have bet. You've each put in $100, and you've each picked a word. And you're sitting there thinking, and you have a word, and that's the secret word. And if I say the secret word, you win the entire pot. And you each have your word. And I'm thinking, you're all going to pay attention. You're going to start asking questions, like, how do you tell time if your word is clock? Or, or whatever. Okay, so anyway, I'm having this thought. It's a little nuts. Okay, so then... Okay, now, we're beginning. So then I have this model. So the model is that there are 2 or 3 secret words. What did I write down here? Oh, so we had, so the thought is, this is the sort of thought, what words would you use if you were now going to bet on what I was going to say? So my candidates for secret words were... I don't know, but maybe you'd have, these are pretty disgusting, aren't they? Are these this one's good at the last 10 minutes, right? This one is getting good at the end. I almost always say this word. I don't know. Do you have any other suggestions? I mean, if you had to pick a word. I mean, not, it's not to be boring. It's not supposed to be the, or something like that, stupid, but it's supposed to be, well, these are stupid enough, but... Okay, so then, you can imagine, instead of just going until you got the first word, you can imagine this thing where there's a bunch of these words like these 4, E, P, H, and L. And that I might, over the course of instead of this, a more sophisticated version, is I might play this game where you might be counting how often I say each of the secret words. So the thing would be either for one of these 4 words or for all 4. How many times during the class will I say that word? And now we might model, we're going to get now, here we come, Poisson process. We might model the number of times that I say one of the words or the word exam, and how it occurs through the course of the time. So we have time. So this is where, oh, this thing doesn't want to go anywhere. But okay, so we have time. We think of, we start off at the beginning of class, and we have an hour and 15 minutes. And at this point, I say exam. And then somewhere else I say exam again. An exam, maybe I say it twice in a row, getting excited about it, and then so forth and here. And then I could be, so I could think of these, and in any one of these, so I could, for each of these, I could be saying these words, and we could think of me as a model. So a simple model for me would be that I'm random, that I'm just making these random utterances, which is sort of the way it seems like. You know, it seems like I'm just making random utterances. And so then you might think, how do you model? So I'm now trying to think of one variation would be that I make just these words, I would say them totally at random. Another version that would be that when I say exam, I'm likely to say it 5 or 6 times, you know, in a cluster, because, you know, it's sort of like there's some dependence. But one model, the simplest model, so this is a standard thing in this course, is the reference is a lot of independence, that there is no, you know, if you had to think of a null hypothesis, that there would be just randomly. You know, that there wouldn't be any clusters. It would just occur. So there might be, as you go through time, a random chance that I say the word exam, and no matter what the history is, independent of the past, I have a random chance to say it again. So I just kind of, you know, at any given time, there's a small intensity that I will say exam. And I do so. And having no memory, I forget what I did, and I just go on, and I might do it again, and so forth. And then I count, well, here's the first time I said it, here's the second, and here's the so forth. I go on like this. So I have a process, n of t, that counts the number of times I said exam up to time t. So I have this counting function, but these times that I say this random. And I'm thinking of it just totally at random, in a kind of idealized sense, so that I don't say exam, you know, I don't do them in clusters, which is going to have bearing, this has something to do with the catching the fish, too, and the other problem. It's just as bad. You might think, and reasonably so, that I would say it in clusters. When we talk about going fishing, you might think, well, you don't catch fish independently, you catch them in clusters and so forth. And yet, a simple model for how a lot of things happen through time, events, is to have them happen independently. So you might actually have exams happening in this way. I mean, my saying the word, not giving exams, my saying the word exam or probability, or each of these might be separate counting processes, random processes, which we could call a Poisson process. Now, the odd part about this is I haven't said anything in my discussion about Poisson. I just said that the events that we're talking about that occur in time happen randomly, totally randomly at a constant intensity. And yet it's called a Poisson process for good reason, because it's going to turn out that the distribution of the number of these events in any interval is going to be Poisson. But that is sort of, it either can be taken as the definition or something you derive. But the idea is that these events in time are sort of totally random. They're independent. You know, if you think of here, what happened in the past has no bearing on the future. What happens in separate intervals is supposed to be totally independent. It's a model for how things happen in time where you assume there's a maximum independence. But there really isn't any clustering. There's no information. That's often an idealization. Okay, so then it turns out, but this is one of the things that's, if you want to know the probability that n of t plus s minus n of s equals k, this is the number up to time t plus s and the number up to s. So this is looking at s and s plus t. This is length t, right? up to s, because this is from 0 to s, and this is 0s, and this is 0 to s plus t. So this is the number of events that occur between s and s plus t. Okay? And then this is going to have this and this lambda is the intensity at which these, if we're talking about, let's call this n sub e, for the number of times I say the word exam between time s and s plus t. Now, s doesn't appear here, so that says in every interval of length t, there will be the same probability of having k of these words spoken, right? That's sort of the thing. There's the Poisson distribution. And notice the lambda is the intensity. So this is that small intensity that I talked about of saying that word at any given instant would be, this lambda would be the intensity. And here it is here. And then the probability, this is Poisson and has mean lambda t. So here, instead of just a Poisson, the mean is proportional to the length of the interval, which makes sense. If you double the interval, you're going to double the mean, and you're going to affect probability. So this is a standard Poisson distribution, except the mean, which is this part here, is lambda times t. It's the intensity lambda times the length of the interval. Okay? Now, the randomness comes in when we say that if we talk about, if we're sitting here and we have 0 and we have AB and CD, and we say, well, what's the distribution of the number of points here and here? And since they're disjoint intervals, and that everything's at random, everything's independent, the number here and the number here will be independent. So if you want to say this is J and this is K, you're going to have, let's write that down here, you're going to have e to the minus lambda b minus a is the length. Lambda b minus a to the j. That's the probability of having j in this interval AB. And then since they're independent, you're going to have this k. This is the probability of having k in this interval. And since they're independent, it's the product of the two. Now it's important, of course, that these intervals be disjoint. If the intervals overlapped, then they'd have something in common. But you could, if they overlapped, like if we made something, well, that's this. But if I made the interval like this, right, if this was one and this was the other, I could have broken it up to 3 pieces that are disjoint. Right, so this would, then I could talk about, and obviously where they're the same is going to be, they're going to be identical. It's not going to have a different story in the same interval. So if this would be something else, and if you had, you'd have, a different story. But anyway, this is for independence over joint intervals. So then you could think, well, let's see. I'm going to win $500 if he says exam over an hour and 15 minutes if he says exam 7 times. So they would get, you all have your word. Somebody has exam 7 times. Somebody has lunch 5 times, and right, and you think, well, okay. And then you could think a probability model for all these things. Those 4 words are being said randomly. So there would be, in this picture, there would be intensity lambda E, homework, exams, lunch, and what else did I even forgot what the word was. It was some other word. Probability, there's one. How could I forget that? Probability, yeah. That you'd think, well, which one, you'd have your opinion. This weren't actually all the kind of important deterministic data are in these 4 parameters, because this is the likelihood you're going to say these things. If you believe this model, then all the math will follow from these 4 parameters, and of course the length of the intervals that you're talking about. Yeah. Okay. Now, there's two nice things. So on this, let's see. So somewhere you'll see going around is this concise summary, one page about exponential and Poisson. So you should all have this one page. So there's two very nice properties that kind of relate to this. There's the property of thinning and the property of superposition. So let me say something about that. That relates to this. You could think, let me just draw a picture, that I'm going to say secret word somehow. One of those four words, Poisson process, lambda s, it's secret word. I'm going to say one of those, it's at random. One of the four words, it has some rate, lambda s. I mean, it's obvious the rate should be the sum of these four rates, right? But just think of this. Now, suppose the mechanism as follows. I'm kind of totally random, making random utterances. I make, according to a Poisson process, I say one of the secret words. Boom, 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 boom. When I say one of these words, being a random automaton and so forth, I, independently of everything else, randomly select one of the four words with some probability, with a fixed probability. In other words, I take some P-E as the probability of selecting exam as one of the four words. So I first go along and I'm just a Poisson process. I decide at this instant I'm going to say one of the secret words. I then do a random experiment and select one of those four words and say it. Start over, go forward, and until I select another secret word. And then I do the experiment over. I randomly select one of the four words independent of the past with the same probability. And so I'm going to get, exam, but then I'm going to get probability, and then I'm going to say lunch finally or somewhere. But in this case, lunch does not come at the end with any higher probability. They're all, every time there's one of these things done, it's equal probability. I mean, this is no systematic stuff in this thing. Okay, so this is the thinning. You have a process of events, a Poisson process, where each point that occurs is one of four other things. You're going to assign labels. It's going to be either, the secret word is either going to be exam, lunch, probability, or homework. And it's an independent experiment. As a result of that thinning and the nice, beautiful property of all this stuff, the four processes you produce are four independent Poisson processes. You start with one Poisson process, you independently thin, and you get four separate Poisson processes. That happens with almost nothing else. So that's the thinning property. Now, on the other hand, and it better be that lambda s PE is going to be this. In other words, the intensity of this secret word times the probability of selecting exam is going to be the intensity of the exam one. This original intensity, or correspondingly, this is, which is just what you would think. The overall intensity is the sum of the four separate intensities. The probability, therefore, the probability of selecting exam is the exam intensity divided by the sum of the intensities. Right? Just what you would expect. Okay. Now, the other problem is I didn't have to start with this one Poisson process that I thinned. I could have assumed that I had four separate Poisson processes, one for each of the words, totally independent, and they were going on. Like part of me is generating exam, the word exam randomly, and I'm at the same time doing all of this. And they're separate. And then the superposition theorem says that if I add those independent processes, I count the exams and these and all of these, and I add them up. If I add independent Poisson processes, I get a Poisson back. These properties are generally not true for other kinds of processes that you add, thin and superpose. So when I say add, this is the picture. The picture should be obvious. I'd have the exam picture. I'd have the homework, I have the probability, and I have lunch. And then I have down here S. So here's time starting off. So this is occurring like this. And this is occurring. And then here are lunch. So we have a lunch here and here. These are going on. And then the superposition is just, right? It's just putting these points down here, so it's all the points. And so forth, right? So if I have the events of these 4 separate streams occurring in time, and then I make this is a superposition. So a Poisson process is a random distribution of points in time, and when I superpose, I could draw a picture of what a possible realization is like this picture. And when I have 4 of them, possible picture, the superposition is just the points that occur in any of them, right? And this definition is fine for any kind of point process. It's called a point process. Things get point process. I could have lots of point processes. The very special one that's got all the good properties, wonderful things happen, is the Poisson process. But I could have these points distributed in some other random way. But anyway, this is here's the superposition. So if these are independent Poisson, then this superposition will be Poisson. And it'll have the sum of this intensity will be the sum of these intensities, just what you'd expect. So then you could think, how should you, if I say exam according to a Poisson process at rate 2 per hour, and I say the homework at rate 3 per hour, and I say so whatever, and you say which one should you pick? You could think which one should you pick if you have to bet if you're going to win all this pot? You're going to win $6,000 because everybody puts in $100, and the one who gets the thing right somehow, or whatever. You could think about this issue, and I don't know, that gets interesting when you interject questions. When you ask, you can alter the random model considerably by judiciously asking questions like, "Aren't you hungry?" and what is it? It's 12 o'clock. What is it time for now? And so forth. That to change the random behavior. Okay. Well. Okay, well, anyway. There's, so regardless of the probability, there's a certain sensibility, Groucho's sensibility is nice. And you can't escape this. What's nice is you go into Carl Sigmund, he's sort of the other alternative person who does almost the same stuff I do. And he's, teaching a lot of this courses, so you think, well, if I don't want to do this course now. Maybe I'll do the same thing with Carl Sigmund later. You go into his office, and there on the wall is a big poster of the Three Stooges, so that you can't escape the Marx Brothers here. Somehow it seems to be here. Okay, maybe it's time for fishing. I don't know. We can start fishing. Maybe we can start fishing. Okay. Well, I had the feeling last time that when I just launched into the problem that, and we hadn't really started reading about exponential, that was a little abrupt. So now we might start in on the problem. But yes, go ahead.
And the relationship between the lambdas in that case will be the same as the previous case?
Yeah, this is, if there's a lambda for this, and there's a lambda for this, and the lambda for this, and the lambda for this, and a lambda for this, this will be the sum of these 4. And it will be back and forth. But if you took some other process, like we'll be studying about renewal processes, there's a beautiful theorem that says if you superpose 2 independent renewal processes and you get a renewal process, that occurs only if all 3 processes are Poisson. So, I mean, the renewal processes, so there's a bunch of, the thing is really special, this property. Yeah, go ahead.
Same property and superposition period, the lambda s is going to be the same for both? Like, it's going to be the sum of all lambdas of the...
I'm not sure if I'm missing your question. Yeah.
Well, like, for the... When you had this, the thinning property where you had each Poisson process for the superposition occurring at the same time, like, it's different times, and then...
Well, this superposition just, boom, all time. Means that whenever these occur, down here is just the occurrence of all of them. So the superposition isn't at one time, it means the whole thing. This, whatever these are, this is really counting all of them. And then, indeed, the rate will be the sum of these rates. And this will be, and then if you went the other way, you could say, well, if I started with this, I would go the other way, and this point would become one of these, right, by thinning. If I went the other way, I would start with this process and say, oh, at this point, I independently select one of the other four and attach one of these labels, this one, to it. I mean, imagine I start with these points, and I create these. At each point when I have one of these, I pick one of these four with the probability, which would be this over the sum of these four. And I would pick this point. I mean, here I'm showing the realization. This picture, I guess a thing to emphasize is this picture is totally deterministic, right? I'm showing you one possible realization of what might happen. These points might fall on this line in this way. I'm not saying that they, that's to show, which is very useful. That's called, you're looking at a sample path to see what might happen. But then what actually happens, where the points are, is going to happen at random. But if you do the thinning, you'd start with these points and then put these in one of the four lines, depending on what the independent experiments. Did I say anything that was helpful in that? But not what I think. Okay, no, that's okay. It's okay. Yeah. When has one said something useful is unclear? Somewhere here. Oh, we have all these things all. So I want to do there's these handouts. Does everybody, so I guess I should start. Maybe this is not a bad, we'll start. Does anybody need the fishing handout? Yeah, here's the fishing. So let me pass this around. And these others are here. The others, I want to discuss the fishing. The other ones will be here to pick up afterwards. They're here, so you can pick up stuff. So Constantine's going to get to go fishing. Now you're somewhere. Do you have? You could pass forward your fish papers. You've all written on your paper, one piece of paper, your 3 fish that you eat, catch, eat, whatever. You may not go fishing. You eat fish, though. You might not eat fish. If you don't eat fish, you probably know about fish. Okay. I'm thinking this. I guess. Well, I'm thinking it's an interesting issue here. I think we have a good. Okay, well, this sort of captures the spirit, at least part of this. I don't know about the fishing, but right about now we're sensing that we're sensing that March 10th is approaching. Not fast enough, but March 10th is approaching. That is not, if you don't know, that's really good. That's, I guess, good, or maybe it's because you're so buried, it's hard. March 10th is the spring break. That's the Thursday before spring break, I guess. So that's like today, the week before spring break, if you think of it in the most positive way, in the Columbia way, at least the business school. If you're here working hard on Thursday night, you can see that it's the weekend on Thursday at Columbia by the fact that the business school will be shaking. The whole building, yours will be shaking as you go by, right? You're working here, you're grinding away here, and you walk out of mud, and you have to go back to wherever you're going. You go out of mud, and there's the business school just vibrating, right? Okay. Whatever you're grinding on some horrendous homework on Poisson processes and Markov chain, and the thing's going crazy. Okay, so. Because in spring break, to take a change of pace from his intense Columbia experience, Constantine has decided to go fishing during spring break. And he's going to go to Florida. That's supposed to, it sounds good, right? He's going to go to Florida, Venice, Florida, on the Gulf of Mexico. He's thinking about it right now. Maybe that's not such a bad idea. Okay, now, then, what? You thought? No way. Just go somewhere in New York City, somewhere else in New York City. Yeah, you don't have to, you certainly can eat all this fish. You don't have to go to Florida to eat whatever fish you can eat in Florida, surely you can eat in New York. Okay, right? There's no need to go to Florida. Okay, now, right away, this nice story takes a bad turn, right? Suppose that Constantine catches fish according to a Poisson process at rate 3 per hour. Just what you wanted to suppose. Okay, that's setting the problem. Then, we have a whole stream of questions, just like would appear on the exam. What is the expected number of fish Constantine catches in a 2-hour period? A. Expected number of fish in a 2-hour period. We have a Poisson process. The mean is lambda t. So this is the lambda is the intensity, which we have said is 3 per hour. 3 per hour. The time is a 2-hour period. So this is emphasizing that the mean number of fish he catches in this 2-hour period is the direct product of the intensity and the time. 3 times 2 is 6. Right? What is the variance of the number of fish Constantine catches in a 2-hour period? Okay, so this is a Poisson distribution, not an exponential. If it was exponential, the variance would be the square of the mean. If it's Poisson, it's something else. If it's Poisson, the variance is equal to the mean. So all you're remembering, but given what we're doing now, you need to know the exponential distribution and the Poisson distribution backwards, forwards, upside down, in your sleep, all this stuff. So you don't want to be marching through questions like this and thinking you have to find it, right? And you don't want to get confused. You don't want to say, oh, it's a square. The exponential variance is the square of the mean. The Poisson variance is equal to the mean. So in B, the answer is the same, 6 again. But that's just sort of to emphasize, that's all at this part of it's just know the Poisson distribution and the exponential distribution. Okay, what is the probability that Constantine catches exactly 4 fish in a given 2-hour period? So in a 2-hour period, this might be this. Here's a given 2-hour period. And we want to know the probability that he catches 4 fish. This would be, this is in the interval t and t plus 2. Did I say 2? In a given 2-hour period, so between t and t plus 2. Remember, n of t refers to the number in 0t. And when we do the picture of the thing, it's going like this. N of t is the number in this interval from 0 to t. So then, if I subtract these two, I've got the number in between t and t plus 2. Okay, and then this thing that we've written there is just the Poisson, but now it's got a 2 here, because the length, and we've got 4 factorial, but the lambda is 3. So it's, right, the 6 is the lambda t, which here is 2. This is 3, right? This is different from this. Maybe I should avoid confusion. I could have written this. I could assume, so this distribution is independent of s, so I might as well assume I'm starting at 0. So I might have written this this way, where t is equal to 2. That's for length 2, right? And this is just starting at 0 because it's some interval of length 2, and it doesn't matter when it is. So this could be referring to the number of fish in an interval of length t, and where here's t is 2. And that would again lead to this, because the t would be 2. So the lambda is 3 and the t is 2, and then which just Poisson. What is the probability that Constantine catches at least 2 fish in a 2-hour period? Okay, so at least 2. So we know this is the probability of exactly 4, so at least 2 is 1 minus 0, which is e to the minus 6, 6 to the 0, 0, at least 2, and 1 minus, right? That's at least 2, right? The probability 1 minus the probability of getting 0 or the probability of getting 1. And this is just, this stuff is all 1. Okay, so x to the 0 is 1, and 0 factorial is 1. So you could just get this. So don't be put off by that, and this, so you get this thing is just to repeat the probability n of t, now, did I say this right? Less than 2 is the question, right? What is the probability that Constantine catches at least 2 fish? Okay, at least 2 fish is the probability that n of t is 1 minus the probability that n of t less than or equal to 1. And then this is probability that n of t equals 0 plus the probability that n of t equals 1, referring to this piece here, and that's what's written over there. Okay, now you start getting, now's the stuff where part E and F are nice, because then you have to sort of, the point E, part E is nice because you have to start remembering what the model is and separate what the model is from your intuition. We've assumed that the model is Poisson. He's going fishing. He's catching fish according to a Poisson process. It may not make any sense. So what is the question? The question is, what is the conditional probability that Constantine catches exactly 4 fish in a given 2-hour period, given that he catches 23 fish in the previous 2 hours? I mean, reasonable person thinks, well, today's a good day, the fish are biting. If he just caught 23 fish in the last 2-hour period, I mean, this is mostly what you'd think. Surely he's going to catch more in the next 2-hour period than if you didn't do that, like if you only caught 1. Intuitively, that's totally reasonable, but this model doesn't say that. This model says that everything's independent, so the past doesn't matter, and it's the same with as if he caught 0. The model says it makes no difference. Model's stupid, maybe, but that's what the model says. It's very important to distinguish between what the model says and what's realistic. If you were doing this, then you'd say this might not be a very good model. Okay. What is the conditional expected number of fish that Constantine catches in a given 2-hour period, given that he catches 23 fish in the previous 2 hours? It's the same issue. The conditional expected value is the same as the ordinary expected value because it's independent. Then there's a question of thinking about whether the model is reasonable. Okay, let's move to H. The model isn't reasonable. You could test it with a little statistics. Let's move on to H. H is asking a different question. What is the expected time until Constantine catches his 4th fish? Okay, so you're now sitting here, a different question, something kind of different. You're sitting here, here is this Poisson process. He's catching fish according to a Poisson process, and you want to know, here's the first one, here's the second one, here's the third one, and here's the 4th one, and you want to know this time here, what's the expected time till he gets the 4th fish? How long is this? Okay. So that kind of isn't on the table right now from what we've said. However, a key property is that these intervals between successive catching events in a Poisson process are what? How are they distributed? What would be the best possible thing they could be? That's what they are. I don't know, maybe you could think of something better. They are exponential and they're independent. Exponential, everything is wonderful. Poisson is everything wonderful. They're all tied together. Everything's beautiful. Everything happens wonderfully. This is exponential, and these four are all independent. They all have the same exponential. So these four are, this is x1, x2, x3, x4. These are inter-arrival times, if this is an arrival process. These are the intervals between successive points. They're independent and identically distributed exponential variables. So xi is distributed as exponential lambda. Same lambda as the intensity. So the mean of t is 4 over lambda. Each exponential has mean 1 over lambda, because when an exponential has rate lambda, the mean is the reciprocal of the rate. And that rate that goes with the exponential is precisely the rate of the Poisson process. So everything's tied together. And so this t, the time until the fourth one, is just the sum of these 4 times, which are independent and exponential, and the same lambda that goes with this process. So the lambda was catching fish at rate 3 per hour, so this is 4/3. 4/3 hour will be 4/3 of an hour is the expected time it takes to catch 4 fish. Under those circumstances, I guess if we did the questions in reverse order, you would be very impressed to see that he caught 23 fish in the first 2-hour period. You would, if you hadn't already concluded so, you would say the model really is totally stupid. But anyway, that's... Now we have this question. What is the variance of this time until he catches the 4th fish? So this should be, you want to be like a little bit like automatons, and on this point, what is the variance of this? You then think, these are 4 independent exponential variables. Each exponential variable, the variance is the square of the mean. So that's the 4 times, the variance of each one is 1 over lambda squared. So it's 4 over lambda squared. Right? So an exponential, variance of the sum is the sum of the variances when they're independent. They're independent. The variance of an exponential is the square of the mean. And it helps a little bit that you can go back and look in the book or sit down and do it, that you actually can prove all these things and derive them and see that it's done in the book and so forth. But you want to see for yourself that that's true. And it's easy to show, but you want to then also memorize that and so forth and have that clear in your mind. Okay, now, how likely, it's not quite time, but it's almost time to say the word, right? The L word. The L word. I'm beginning to think of the L word, see, that's a non-Poisson event, but we're not quite there. We're not quite there. We're now getting the N word. We're coming to the question for the N word. N word wasn't on the list. How likely would it be that Constantine would catch more than 90 fish in 27 hours? Well, the boat would sink, right? Okay, I don't know. How likely would it be that he catch more than 90 fish in 27 hours? So now it's time for the N word, right? What's the N word? Yes, yeah, thank you. There you go. The N word, right? Normal. Yes. Yeah. So here you can think of things normal in a bunch of ways, but let's see. So what is this question? The probability, we're at J. The probability, number of fish in 27 hours, more than 90 fish. I'm making it strictly more. This is being very precise. Number of fish, this is in 27 hours. T equals 27. lambda equals 3 from before, just as before. Now, if we wanted to know that exactly, we could write down e to the minus lambda t to the k factorial, and sum from k equals 91 to infinity. And just chug this baby, sum this up, and that's the answer, right? Because the probability that this, where this is lambda is equal to 3 and t is equal to 27. Because this is these. So this is the thing directly Poisson. Poisson tail probability. Yeah, that helps. That helps a lot because 1 minus this one, you're not going to do that ever, right? Whereas 1 minus sum to 90 is a big improvement. I mean, this is not possible, and this is possible. So that actually wouldn't be that hard on the computer, with no problem. Little problem, not too much. This has got some items that could be pretty big in here, these things. So, of course, what the N word applies. So this is one way. Whenever you have a Poisson distribution with a large mean, it's approximately normal. One way to see that is the central limit theorem, because the Poisson, let me write it this way, Poisson lambda is equal in distribution to the sum of Poisson lambda over n, k equals 1 to n. So if I have a Poisson random variable with mean lambda, I can always split it up, and it's like the Poisson process. Here's this some plate, I can just divide it up into independent intervals. Then it will be the sum of IID Poisson variables with mean 1 over n of this. So it could be, think of it as a central limit theorem. At any rate, a Poisson with a large mean, the mean here is 3 times 27. Okay, yeah, 81, right? So the mean is huge. I mean, compared to what you need. A mean of 10 would be fine. Certainly a mean of 81 is fine. So this thing's Poisson, and it's approximately normal. So we're doing this. We're probability n of 27 greater than 90. Now, what we do is we subtract the mean and divide by the standard deviation to scale this to have mean 0 and variance 1. So we first say, oh, well, I'm going to subtract the mean, which is 81, from both sides, so nothing has changed. And then I'm going to divide by the standard deviation. The mean, whoever made up this problem was thinking ahead. The mean is 81. Therefore, it's Poisson. The variance is the same as the mean. It's 81. Therefore, the standard deviation is 9. So we don't have, we could actually, we're not having to do anything tough. So when we divide by 9 here, we have then this thing is, this is a slightly confusing notation. Okay. This is the Poisson number in this interval of length 27 minus the mean divided by the standard deviation. This thing is approximately standard normal, mean 0 and variance 1. This is exactly 1. So approximately we're asking what's the probability that the normal, a standard normal, is greater than 1. We look on Ross, page 81. Right? You get some answer like 0.16, something like that, right? I guess, yeah, something like that. I mean, this is bigger than 1 standard deviation, you know, like 1 standard deviation is not too surprising, so it's not crazy like some of the things. Okay. How likely would it be that it would take Constantine less than 27 hours to catch 90 fish? Less than 27 hours to catch 90 fish. What if you did that directly? You might think of the thing. You might do something like this. You might less than 20. Let me just write this way. To catch, he wants to catch 90 fish. So that's 90 fish in less than 27 hours, right? Where this is the interval until he catches the first fish, and then these are the successive intervals between catching successive fish. So how likely would it be that it would take Constantine less than 27 hours to catch 90 fish? This is the time it would take to catch 90 fish. It's a sum of 90 IID exponential lambda variables. We can apply again the central limit theorem where we use the mean and variance of this, because these each have mean 1 over lambda and variance 1 over lambda squared, because these are exponential. So we could write, we call this S90 for the sum of 90. That's exactly probability S90 less than 27. We could subtract the mean, which is 90 times 1/3, right? Mean is 1/3, and 90 is 30, and then the 1/3 is the mean, 1/9 is the variance, and of each one, and there are 90 of them, means that the variance is 10. So this would be square root of 10. And you'd get, this is approximately normal 0, 1, less than minus 3 over square root of 10. And this is sort of less than minus 1, approximately. And this can be related. It looks a lot like the previous problem. You can actually relate it, but it comes out by this reasoning slightly different. In other words, this probability normal 1 being less than minus 1 is very much similar to being, that's the same probability as normal 1 being greater than plus 1. And that can be, you can actually relate these. But the main thing to observe is, when we looked at the previous question, we were looking at the count of the Poisson number. The Poisson number with a large mean is approximately normal. At the same time, the sum of these times that are IID is approximately normal by the central limit theorem. So you could also ask the question the other way. It's again just using, in both cases, just using the normal approximation, one for a sum of IID random variables and the other for the Poisson distribution. And then once you know it's approximately normal, you just subtract the mean and divide by the standard deviation, calculate. Okay, so we're actually going to do this. Somehow it seems slower today, even though this is just as long as the last one. Last time I seemed like I was racing. But you're not. Unfortunately, you would be aided if you were doing this contest and you were going to win one of these prizes. But anyway, here we are, K, L, L, L. Suppose that Constantine catches exactly 4 fish in a 2-hour period. Exactly 4 fish. What then is the probability that he catches all fish in the first 30 minutes? So there's a 0, 1, 2, half, and we're told that in this period he caught 4 fish in this whole period, and what's the probability that he catches all? Well, we told he caught 4 in this interval. What's the probability that all 4 were here? This property is also not on the table. I guess a point of view to think about this is, what would be the best possible thing you could think of? I hear a mumbling of in order to think about this problem, what kind of situation would make this easy? And what would make it easy is exactly what's true. In other words, you want to, there are 4 fish, they're caught 4, so they know there's a total of 4. If there was only 1, it would be easy, right? If there was 1, the probability any 1 would be in here would be 1/4. No issue, symmetric. All the intervals are the same. But now we want to know that they're all 4 here. Yeah, Rob. This is also 0 fish here, isn't it? So, but you've conditioned on this. You know there's exactly 4. So it's true, if you wrote this out, you would write something like probability n of, let's call it 1/2, equals 4, and n of 2 minus n of 1/2 equals 0, right? And then over probability n of 2, I'm now just grinding, right? I'm now saying I don't know anything special. So if I just didn't know anything special, I'd say, well, the probability of getting 4 in this half-hour interval and 0 in the remaining, and I'd divide by the probability I get 4 total, and I'd compute the conditional probability of getting all 4 here, given that I got 4 total. So this is following. I'm interpreting your question is, can't we just compute this? Sure. So what I'm looking for, though, is to think about the high-level story that's going to kind of say what's going on, that's going to mean that this has something simple. It's not just a bunch of exponentials and factorials. It's actually going to become something very simple. And it's going to become, if there's 1, if we know there's 1 and we know the probability is 1/4, right? If there are 4, what would be nice? It would be this would be nice, right? If the 4, so the thought is, if there are 4 fish, if there are 4 events in an interval, the nice property would be that the 4 fish are distributed independently and uniformly. Right? It's sort of clear that each one should be uniform, because there's no favoritism of being anywhere in the interval. So if you condition on any number of Poisson events being in an interval, conditioned on that, then where those things, the location is each one is uniformly distributed and they're all independent. So this is the same as if there are 4 independent uniform random variables. So each one would be in here with probability 1/4. That makes sense. But then they're all independent means just that all 4 have to be there, which is just this. And now if we do this, we're going to see that we get e to the minus lambda 1/2 to the 4th, e to the minus lambda 3/2 to the 0 factorial, 4 factorial. Then we're going to get e to the minus lambda 2 to the 4 over 4 factorial. Right? I'm now carrying this all out, and when you do that, the 4 factorials, these are going to cancel, and then this is going to become this, and then the lambda half, the lambda, this is going to be I guess I'm getting, somehow I should be doing this right. I should be pulling this thing out, and I'm going to get 1/2 to the 4th if I do this right. Lambda 1/2 to the 4th. I'm getting this is 1/4. Wait, let's see. So lambda, it's a half long. This should be, this is half, but wait, then this, I have 2 of them. No problem, right? Right? And I got 2 here and 2 here. Yeah. This is divided by this is 1/4. Yeah, this is where, this is an illustration of why it's, I guess this is an illustration of why it's good to understand what the property is at a high level. right? I mean, I'm now doing this, cranking through here. If I didn't know what, I mean, right away I know what the answer is. That's much better than cranking through here, because if I do that, I may screw up easily, right, if I'm just depending on doing arithmetic. But conceptually, I know the answer in advance, right? I know this is the answer. And yeah, sure, I get there, I guess. With your help, I get there by grinding. But it's actually convenient to know the structure. And actually, if you look at that one page, that concise summary, it's saying all that stuff. There's something that says, if you have a bunch of Poisson events, if you condition on there's k in this interval, the k are uniformly distributed, their location, and independent. Which is pretty amazing when you think about it, that those things all happen. All the good things that are on that page are pretty much unique to this model, which is why this model becomes very easy to use. You can calculate everything, and so it becomes a reference case. So that's why it's got a prominent place in the course and in the book. Well, actually, this last part, you might think about this yourself, is now things are getting, we want to make things more interesting, and Constantine catches, we now pay attention to what kind of fish he catches. So one of three types. And now he catches each type with a certain probability. So we're coming back to the thinning. We have a catching fish according to a Poisson process, but each fish is some kind with a certain probability. So then the processes that record the number of each of the fish he's catching become three independent Poisson processes. Then, knowing that, any questions you have, like if you condition on what he does, how many grouper does he catch, given that he catches, what is he catching, grouper, snapper, if you condition that he caught 17 snapper, it's going to have no effect on how many grouper he caught, because the two processes are independent. And each of the processes has independent increments. What they do in 1 hour has nothing to do with what happens in the next, and so forth. So it's this repetition of the same thing. The L word. Okay, let's stop. So pick up things. If you didn't get homework back, exams back, pick them up.